not much left. Um, really, there are just 3 lessons to go on the third major PDE. And after spending so much time on heat equations and wave equations, now it's Laplace's equation. And in the next 2 lessons, so Wednesday and Monday, I'll talk about specific problems involving Laplace's equation on certain domains of interest and show you how to solve those. And then we'll be done. So I will have one class one class period set aside for a review for the final. Final will be comprehensive. There'll be 3 problems on it from the new stuff that I'm about to cover this week and next. And then there will be some problems on the old stuff. But similar in nature to problems you've seen from the first 2 tests. Okay, so I'll be putting out actually, let's check what I've done in the past for as far as practice goes. Try something to this here. Okay. So there'll be a couple problems on the new material and Laplace equations and the rest of the old stuff. I will have a practice test that covers the whole thing. Okay. So we've been there, there'll be a fair amount of review there. So really we really need 4 class periods to cover everything. Once that's done, we don't come here anymore. So, and then at that time I will post the final. Everything is due Thursday, May 12th. That's Thursday of finals week. So that's when the final will be due also. But I guess this will be finishing early. There's no reason why I can't get it early start. And get it out of the way if you prefer. Okay. Are there any questions? So for test 2, I graded all the ones that were turned in over the weekend. Seems like for the most part it went well. So you should be able to see comments in Canvas for what went wrong. The way I did the scoring was I just made every problem worth 15 points. And so the maximum possible total was 120. So if you have any questions about point deductions, you just let me know. Well, do any of the 3 students in attendance have any questions regarding the test? Okay, and then as a reminder about homework, there are 9 assignments total, and all of them should be posted in Canvas by now, or on the external site. And but yeah, so the lowest 2 of those will be dropped. So make sure you have at least 7 assignments in, just so you don't have any unnecessary holes in your grade. Now the Laplacian, but we've dealt with the Laplacian in some form all semester long, but most of the time it's only been one dimension, where Laplacian just reduces to uxx. Or generally, it's just the sum of all the second partial derivatives of u that are with respect to the same variable twice. So here we have it in 3D, uxx plus uyy plus uzz. So we see it play a role in the heat equation and the wave equation, but now we're interested in time-independent PDEs, where the only differential operator feature is Laplacian. And keep in mind the notation that's used for it. The Laplacian can be defined as, I'll fill that in here, the divergence of the gradient of u. So that does work out to be the Laplacian. But because we have the same symbol used for gradient and divergence, that's why it's often written this way. Even though this doesn't really make sense, but it's a frequently used notation. And we also have the right side up delta describe Laplacian. Okay, now if we take a look at Laplacian, even just focusing on the simple one-dimensional case. So here I do a Taylor expansion. And then if I take this, expand, so both sides of this equation, and I integrate over an interval that is centered at x naught. So the interval is centered at x naught and has a radius, or if you will, of h. Then here's what happens. Okay. All right, so then we get this, here u x naught is just a constant. Any derivatives are evaluated at x naught. So we can just pull those out. And then what's left is a polynomial in x. So certainly that'll be straightforward to integrate. But for convenience, I do a change of variable. I define s to be x minus x naught over h. And the reason for that is it maps the interval x naught minus h, x naught plus h to the interval -1 to 1. Just to make the integration more straightforward. So as a result, these factors like this h squared here, this h cubed here, these come about from making that, okay, in this case it's an s substitution rather than a u substitution. And then this integral right here, from -1 to 1 of s ds, can anyone tell me how can we know the answer to this value of this integral without actually going through the motions of integrating? How can we tell what this one is immediately? It's a trick, if you will, that's supposed to be taught in Cal 2. May have forgotten.
It's like an odd function?
Yes. Any polynomial of odd degree, of all the odd degree terms, is an odd function. And the integral over an interval such as this, from -1 to 1, of an odd function is what?
0.
It's 0. Yeah. Whereas here we have s squared, it's not 0, but we can replace it with the integral from 0 to 1 of 2s squared, because of symmetry. Which, if you're doing this by hand, is less mistake prone. So this term is gone. So now what we have is, okay, so we have 2h times u at the center of the interval, and this term involving Laplacian. So now, if I divide both sides by 2h, then the left side, this divided by 2h is the average value of u on this interval. So the average of u is equal to the value of u at the center plus this term involving a Laplacian. And then there will be other terms of a higher degree in h. So here's how what this equation tells us. That if Laplacian is positive, then u is smaller than the average of its neighboring values. Because if Laplacian is positive, so this term is positive, this average plus, the value of u at x naught, the value of u at x naught plus something positive gives you the average. Therefore, the average has to be greater. Similarly, if Laplacian is negative at a point, then the value of u at that point is greater than average of its neighboring values. And finally, if Laplacian is equal to 0, but it's equal to the average. Okay. Now, here I just focus on the one-dimensional case, just because the integration is easier to handle. But you can work out similar results in higher dimensions. For example, in 2 dimensions, if you're integrating over a disk of a center x naught, y naught, and radius r. Or if you are in 3 dimensions, you're integrating over a ball, a certain center and radius. Okay. In fact, here we have 2-dimensional case. So I'm performing a multivariable Taylor expansion. So u is equal to its value at the center of the expansion, x naught, y naught. And then we have these terms involving the first partial derivatives and then the second partial derivatives. Now, for convenience, notation-wise, so I should write this in here. Any derivatives that we see here are evaluated at the center of the expansion, x naught, y naught. Okay. Otherwise, this expression would get too cluttered. So then what I want to do is integrate both sides of this equation over the disk that's centered at the point x naught, y naught, and the radius is capital R. And so it makes sense, given the shape of our domain, to work with polar coordinates. Now, the derivatives are all evaluated as select point. So I don't have to worry about converting those to polar coordinates. I can just, they're constants. You can pull them out of the integral. And now I have all these integrals that have been converted to polar coordinates. Note the extra factor of r that has been included in here. And fortunately, some of these integrals will go away. For example, this first one, integral from 0 to 2 pi in theta, 0 to capital R in r cosine theta, also times r. This can be separated into a product of 2 integrals. One is r squared dr, and the other is cosine theta d theta, but this integral of cosine from 0 to 2 pi, that's going to be 0. So this whole term is going to go away. This term will also go away. And this one also, that's worked out down here. Again, I can move things around, and I get the product of an integral with respect to r times the integral with respect to theta. And this right here, this integral can be worked out by u substitution. I can let u equal to sine theta, because then du is cosine theta d theta. So then I can take the antiderivative for that one. And here again, I plug in the limit 0 to 2 pi, I'm just going to get 0. So all the terms involving first partial derivatives go away. All the terms, this term involving the mixed second partial derivative goes away. What's left? The uxx and uyy integrals, and involving the Laplacian terms. So for this one right here, I have r squared cosine theta r d theta. So I do the same thing. I write it as a product of integral of r, integral with respect to theta. But this one, when I integrate this, it's non-zero. I'm here using a trig identity. Cosine squared theta is 1 plus cosine 2 theta over 2. So here I get something non-zero. And for the other similar integral with sine squared theta, it's going to work out exactly the same way, except here I'll have a minus. But that doesn't affect the value of the integral. It's still going to be pi r to the 4th over 4. So once I take all of these results and incorporate them in here, here's what I get, that the average value of u over this disk is equal to the value of u at the center plus this term involving Laplacian. So once again, if the Laplacian is positive, then value of u at the center is less than the average of its neighboring values. And then similarly for the case of Laplacian being negative or 0. So we get the same relationship as in 1D between value of u at the center and the average of its neighboring values in however many dimensions. So here's the role that Laplacian plays in PDEs that we've seen. So what this is saying is that if the temperature at any given point is less than the average temperature surrounding that point, that means that U is going to be concave up. Therefore, the temperature at that point is going to increase, which makes sense because eventually the temperature should converge to some ambient temperature, at least absent any effects from external sources. Similarly, if the temperature at a certain point is greater than average surrounding temperatures, then temperature profile will be concave down at that point. So uxx will be negative, therefore ut will be negative, therefore the temperature u will decrease over time to converge to an average temperature. If the temperature at a certain point is equal to the average, then nothing will change. For the wave equation, then, so we're dealing with a vibrating string, for instance. If we're in 1D or a drum head, which is in 2D. So think about the vibrating string case. That if the displacement at a certain point is less than the displacement at neighboring points, then the string is going to accelerate upward because the second derivative will be positive, you'll have concave up. If ever UTT, which is the acceleration, will also be positive. And finally, if we forget about any time dependency, and it really, this is like, you think the steady state version of the heat equation, where UDT becomes 0. So a solution, U of Laplace's equation, at any given point is equal to the average of its neighboring values. close relative of Laplacian equation is Poisson's equation, where we have z Laplacian equals 0, it's equal to some function. The minus sign is really a convention. It's just so the differential operator, it's often written this way, instead of actually putting the minus on the left side. Okay. Then the differential operator minus Laplacian has positive eigenvalues. When we solve it numerically, that leads to a matrix that is said to be positive definite, which has some nice properties. So it's not an essential feature of the equation, but it's often written in this way. So the application of Poisson's equation is to describe electrostatic potential. So function f here represents the charge density in that setting. Or if you go back to the heat equation, where we have steady state temperature, function f represents a heat source. UDT is 0 in this case because it's steady state. We have the rest of the heat equation with its external source, or heat sink, depending on the sign of f. The Laplacian comes up in this PDE too that we haven't talked about, the Helmholtz equation. We have seen this come up from separation of variables for time-dependent problems, but the Helmholtz equation by itself is also of interest for certain wave propagation problems. Okay. Now, the problems involving Laplace's equation that we'll be seeing later are all in domains that are related to a circle. For example, solving Laplace's equation inside a circle, where you're specifying a boundary condition on a circle. It's called the interior Dirichlet problem. That'll be the subject of Wednesday. Or solving Laplace's equation in a domain outside a certain circle. Again, the circle itself is where you pose a boundary condition. It's called the exterior Dirichlet problem. And finally, solving Laplace's equation in the region between two concentric circles, in other words, within an annulus. So then you're posing boundary conditions on both circles. So, for problems on domains like these, it's quite cumbersome to leave Laplacian in the form that we've seen here today, like uxx plus uyy in 2 dimensions. We would like to be able to work with in a coordinate system that is appropriate for the domain on which the PDE is defined. So, in other words, we want to work with, for a problem I just described, we'd like to use polar coordinates. That's what I'll focus on now, is how do we get the Laplacian, the 2-dimensional Laplacian in polar coordinates. So, remember from Cal 3, here are our polar coordinates. X is our sine theta, y is x is our cosine theta, y is our sine theta. And then the conversions, so going from Cartesian to polar, as opposed to polar to Cartesian. This equation here, tan theta equals y over x, for a given fraction, y over x, does not have a unique solution. If it chooses the solution theta corresponding to the quadrant in which the point xy lies. So that's why the equation is written this way. As opposed to simply doing theta equals inverse tangent of y over x, that may not be the correct angle. Okay. So, what I do, I'm going to start with this formula right here, r in terms of x and y. I want the derivatives of r and theta with respect to x and y. That's going to help me get the Laplacian in polar coordinates. Keep in mind that x and y are independent variables. So here's this straight chain rule, and simplifying where we can. Then I want to express this in polar coordinates because that's what I'm ultimately when I express the Laplacian, any traces of x and y need to go away. Or just left with r and theta. All right. So dr dx simplifies to just cosine theta. Now, to get theta, derivative of theta with respect to x, I'm actually using implicit differentiation because theta is implicitly defined by this equation right here. So if I take the derivatives of both sides with respect to x, okay, by chain rule I get secant squared theta d theta dx. If I take a derivative of this side with respect to x, so now that I have this equation, I'm going to take the secant squared theta and move it to the other side, which is going to give me this cosine squared theta up here because secant is 1 over cosine. And then minus y becomes this. And then the x squared down here, written in polar coordinates. Simplify as much as possible, and this is what we get for d theta dx. And then I repeat the process to get the derivatives of r and theta with respect to y. So I don't repeat those steps here, but they're analogous to what I've just shown you here to get these. There's even certain symmetry between them. Any questions up to this point as far as first steps of the conversion? It's actually quite a thing. Because now I need the second derivatives of r with respect to x or y. So here, for instance, I have Rx is cosine theta. So now I can take a derivative of both sides of this equation with respect to x. I'll get Rxx on the left side. Here I'll get minus sine theta, d theta dx. Fortunately, I have d theta dx. So this actually didn't involve very much. So we have it there. And then similarly, I take a derivative of both sides of this equation with respect to x, and use the fact that I have d theta dx. Okay. Well, something's puzzling me here. I hope this won't be an issue in my notes that I have later. Okay. I don't think a factor of 2 should be there. Surprised I didn't catch this last year. Okay. If I actually go across the doing it, so oh, yeah, okay. This is what I get for trying to do too many things in my head. All right, I'm actually going to show you a little more about what's going on with this one. There's a little bit more to it than for instance, dang it. For example, doing the rdx, okay, or rxx. All right, so like I said, take a derivative of this with respect to x, but what am I going to need to use to take this derivative with respect to x that I haven't had to use so far? So this differentiation is a little more complicated than the ones we've seen up to this point.
You have to use the square root of x squared plus y squared?
No, we don't have to use that, thankfully. In terms of differentiation rules,
We're just differentiating with respect to x, right?
yes. Yeah, so I've got to differentiate this with respect to x. Quotient rule, because r and theta both depend on x. Okay, so how does that work out? So we have, I'll just pull minus up front, so r times the derivative of sine theta today with respect to x. Oh, wait, that does not belong here. It belongs in the numerator. Okay, so r times sine theta with respect to x minus sine theta times the derivative of r with respect to x all over r squared. This is what the quotient rule gives. So now if I continue that, okay. Well, derivative of sine theta with respect to x should be cosine theta times d theta dx. Rx, the r dx is cosine theta. Okay. And then d theta dx is minus sine theta over r, which is going to cancel with the r here. So now I'm going to have, okay. So now I'm going to have, so this whole thing is going to become minus cosine theta sine theta. Here again we have minus cosine theta sine theta. So those terms add together. And then the minus will cancel with a minus over here, thus leaving us with this. Okay, so let's fill in one more step just to make the notes a little more complete. All right, so the theta dx is minus sine theta over r. So from there you can see how once everything is simplified as much as possible, that is what you get. Okay. And then RYY is not much of a problem because we just have to take a derivative with respect to y. Theta YY, taking a derivative with this respect to y, will also require a quotient rule, so it'll work out much like this one. Okay. Well, I'll stop. Any questions about this? Now that we have the first and second derivatives of r and theta with respect to x and y, so quite a few derivatives to work with. Now I turn to, I really want to write uxx and uyy in polar coordinates. So for to start with ux and uy, here I'm just using chain rule. So du dr dr dx plus du d theta dx. And I have all derivatives of r and theta with respect to x or y, so I'll just fill those in. So now I've expressed ux in terms of du dr and du d theta, because I want to have only derivatives of u with respect to polar variables in my final result. So this will help me get there. So ux is now entirely polar coordinates. And I do the same thing with uy to get it entirely polar coordinates. Now, okay. Now, what's funny is in my LaTeX document for what I'm about to talk about here, I have a comment to myself in here: do not do it this way. And I think I know the reason why, but I think it'll be all right. We'll see. Okay, so what I actually do for uxx, I actually go back to this point. I take a derivative of all this with respect to x. Okay. Now, and I think what I might need to do is include some additional terms so that there are no loose ends. Because if I'm going to take a derivative of this, for example, just this term with respect to x, I have a product here. So I need to use a product rule. Now, so for instance, here I'm going to have u rx, rx, and that's what I have here. And then the other part will be ur, and then rxx, so that's here. If I do the same thing over here, take a derivative of this with respect to x using a product rule. So I have u theta x down here, and then theta xx over here. So far, everything's fine, if ugly. Then, all I've done from this step to the next one is just change your differentiation. So u rx can be written as du dx with respect to r. Here, u theta x can be written as ux with respect to theta. And the reason for that is I have formulas for ux already. Again, this one. So I'll go ahead and put those in. And that's all I've done to go from here, from this step to this step. It's just fill in the formulas I have for ux. Again, so far, everything's fine. It's messy. Now, from here to here is where things get off the rails a bit. Because I have to take a derivative of this whole thing in parentheses with respect to r. And each term in here is a product. So I would have to use a product rule on each one of these terms. So taking a derivative of this whole thing with respect to r should give me a total of 4 terms coming from here. Same issue over here. I should get 4 terms from this. Then I take a derivative of this whole thing in parentheses with respect to theta. And then I still have these 2 terms here, which, as you can see, just carry over directly to the next line. So I should have a total of 10 terms. But, okay, and there are only 9. But let's see what happens. All right, so take a derivative of this with respect to r. I will get u r r, rx, rx. All right, that's what we have here. Next I have ur times the derivative of rx with respect to r. But that would be rxr. But that's the same as the derivative of, that's the same as rrx. So I take a derivative of r with respect to r, take its derivative with respect to x. So that wound up down here. And I'll explain what happens to that in a moment. Then over here, I'm going to have, from product rule, u r theta, theta x rx. And then I have u theta, theta xr. And that winds up down here. Okay, this term just copies directly. Here, product rule again, u r theta rx theta x, which is the same as this term that I got earlier, plus the 2. So product rules produce one term from each that are identical. Go ahead and combine them. And then we have ur rx with respect to theta times theta x. Okay. I think something's missing here. Oh, yes, there is. All right. This term should have a factor of rx coming from here. This term should have a factor of theta x. And I also have ur rx theta that goes down here, and then u theta theta x with respect to theta that goes down here, but it is missing a factor of d theta x. Okay, and then this term goes directly here. Okay. Now, all of these terms on the second line are actually 0. Reason why is I have rx with respect to r is the same as derivative of r with respect to r, which is 1. Take a derivative with respect to x, which is 0. So that's why this goes away. And it's also why this goes away. I can write this as derivative of theta with respect to theta, which is 1, take the derivative of that with respect to x, which is 0. Here, derivative of theta with respect to r is 0. Theta and r are independent variables. And here too, derivative of r with respect to theta, that is 0. So then its derivative with respect to x would also be 0. And this term should also have a factor of theta x. Okay.
For clarification, why is the derivative of r with respect to theta 0?
Because they're independent variables. It's kind of like you're taking derivative of x with respect to y.
Okay.
Yeah. So all these go away, and we can focus on what's left and use the formulas that were worked out earlier for r with respect to x, or theta with respect to x. And we have derivatives of u with respect to only the polar variables, r and theta, which is what we want. So that is filled in here. So now we have uxx in terms of derivatives of u with respect to the polar variables only. Then we do the same with uyy, and that essentially plays out the same way. I'm not going to repeat the details here, but it's all analogous. And this is what we get. And notice that the expressions are very similar. Because now we're going to add these to get the Laplacian. We want uxx plus uyy, that's Laplacian in Cartesian coordinates. So now we add these together to get the Laplacian in polar coordinates. Well, here we have cosine squared urr and sine squared urr. Well, cosine squared plus sine squared equals 1, so these terms combine to give us just urr. These terms cancel. These terms also cancel, so that's convenient. Here too we have sine squared theta ur over r plus cosine squared theta ur over r. So you add those, and we get just ur over r. And same thing over here, that gives us u theta theta divided by r squared. So sine squared plus cosine squared equals 1 all over the place. And the really ugly expressions we had earlier, that's something that's not so bad. That's the Laplacian in polar coordinates. But those Laplacian is not defined at the origin, r equals 0, where a polar coordinate system has a singularity, unfortunately. For cylindrical coordinates, which is just polar coordinates along with z, Laplacian is uxx plus uyy plus uzz. So here we have the same polar Laplacian as before, and we just add on uzz. So it's not very interesting. At least it's easy to get once you've done polar. And then if you were to go for an even more monstrous chain rule exercise than what I showed you, you could get the Laplacian in spherical coordinates. That's all this. Okay. And I think what happened last year when I was covering this, that I think I managed to get myself confused or so, or something like that, working out what I just showed you for polar coordinates. And I ended up just doing it a different way, which, as you can see, is still tedious, but one could argue might be easier to make work. Here I have a formula that actually did work out previously for ux. So if I just take that and fill that in here, so that this is ux, take a derivative of that with respect to x. But taking a derivative of anything with respect to x is the same as taking a derivative with respect to r times rx plus the derivative with respect to theta times theta x. And rx and theta x are known, so I just filled those in here. Here, I'm taking a derivative of everything that's in parentheses with respect to r, and then here I'm taking a derivative of the same thing with respect to theta. But the nice thing is everything in here already is a function of r or theta. So things work out a little more nicely. I mean, there's still quite a few terms here, but and of course you're going to get the same result. But doing it this way, at least in my possible state when I'm actually in the middle of class, where that's the problem with that when you're in the middle of actually teaching, your IQ plunges, and I think that's what happened a year ago. This worked out more nicely. I think what I wanted to do here was hold off on including all these formulas that have been worked out. Just have something that's more general in terms of taking finding a general formula for uxx in terms of derivatives with respect to the new variables. Because everything I've shown you up to this point does not take into account at all the relationship between x and y and r and theta. It's only when we get down to here, this last step, where we actually use these things. Which means that a formula like this can be helpful for some other change of coordinates in 2 dimensions. So it's a bit more coordinate agnostic in that sense. Whereas here we made use of what we know about polar coordinate system immediately. But it made algebra or calculus a little bit nicer. Or the calculus certainly. Okay. So when we go to solve Laplace's equation, Laplacian of u equals 0, for problems that we're going to consider in the next couple of lessons, we're not going to be dealing with uxx plus uyy anymore. It's just going to be this. And what we'll see is we're actually going to use separation variables again. Just with different ODEs resulting from it. But a lot of the same principles that were helpful for a heat equation or wave equation will still apply here. And whereas before we did separation variables to get an ODE in x and an ODE in t, now we're going to get an ODE in r and an ODE in theta. Okay, so I will show you all that on Wednesday for the interior Dirichlet problem. And then similar problems on Monday, and then it'll be done. Any questions about what we've seen here? You can take a look at what we've done homework-wise. Okay. For this lesson, this real lesson is just going to be, okay, here's a PDE, go solve it. 31. Okay, I assigned problems 3, 4, and 6. Okay. Oh, wow. Apparently I must have been feeling really sadistic when I made this homework assignment in the past. Okay, well, so there's 3 problems. Okay, I'm gonna unshare and reshare. Okay, that's for lesson 31. The first 2 problems, there's not much to those. So really you're looking at the Laplacian that's given in polar coordinates, what I just derived, for problem 3, and then Laplacian that I've shown you in spherical coordinates. And what does Laplacian's equation look like when you have certain simplifying assumptions about the behavior of u? So if u depends only on r, if u depends only... Now, one notation thing, looks like, if I look at, okay, here's the Laplacian, okay, there's cylindrical coordinates. So this part here is polar coordinates. And then here, the author has the Laplacian spherical coordinates. Using r again as a radial variable. In my notes, I use the Greek letter rho for a radial variable in spherical coordinates. So rho is equal to square root of x squared plus y squared plus z squared. Here the author uses r for both. I think one reason why a lot of people use rho for spherical coordinates is that r is just square root of x squared plus y squared. But you don't say r is equal to this in this case, this in this case. So keep that in mind, that there's a slight notation distinction. And then for the last problem, transform three-dimensional Laplacian to spherical coordinates. So, and I just said that was an even more monstrous chain rule exercise. This is where you keep in mind that the lowest 2 homework assignments are dropped. But someone really wants to do that, then knock yourself out. So I mean, you follow either approach that I did for polar coordinates. It's just more of it. All right, now we're calling that those two homeworks are dropped. I don't feel so bad, but dang. Okay. So if someone's really bored, they can lock themselves in a room and work it out. Okay. So there you have it. And then those get these last 2 lessons over with, and that'll be it.